And the last characteristic that we were going to prove, or end up proving today about parallelograms, is if the diagonals are drawn, they will always end up bisecting each other. So we're going to start off with a parallelogram. We're going to draw in the diagonals, and that these diagonals have a special relationship with each other when they meet. And that is, they are supposed to bisect each other, which means they got to cut each other in half or meet in the midpoint, however you want to think of it. So there's the picture that I'm going to represent. What I want to end up doing is somehow proving that this segment is exactly the same as this segment, because if they're same in length, they had to be cut in half or bisected. That this segment and this segment get cut in half, which means they're going to end up being bisected as well. And in order to do that, what we're going to do is we're going to prove that the top triangle, so I'm just going to shade it, has to be congruent to the bottom triangle. And if that's true, then their corresponding parts, the blue parts have to be congruent, and the green parts have to be congruent. So that's what we're up against, and that's what we're going to try to do and prove in this proof. So we kind of have a general idea. Now we're going to get more specific. I know that this angle 1 has to be the same as this angle 2 because it's a parallelogram, which means the opposite sides are parallel, which means angle 1 and angle 2 are alternate interior angles. So I'm just going to record that. Angle 1 has to be congruent to angle 2 because they're alternate interior angles, and we have our alternate interior angle there. The second thing that I know in these triangles as well is that angle up here, and I'm going to call that angle 3 and 4. And this one down here is 4. For the same reason, we know that angle 3 has to be congruent to angle 4, so I can do a ditto mark on that. So we know we already have two angles of one triangle equal to two angles of another. Now, there's nothing saying that we couldn't have used these vertical angles here, but another angle isn't going to help me to prove that they're congruent. What I need is the length of the side. So the length of the side I'm going to grab is the sides that are in red. Now, because it's a parallelogram, I know that the opposite sides of a parallelogram are always congruent. So now I know that AB is always going to be congruent to DC because they're opposite sides. So we write down that fact that the opposite sides of a parallelogram are always congruent. So now what I've identified is I have an angle and a side and an angle in both of those triangles. So now our triangles have to be congruent through angle, side, angle. So triangle, make sure I label them right. And I'm going to need another point here in order to prove that they're, or in order to name them. So I'm going to call it an M, and the M stands for it's going to be the midpoint. And the midpoint means it's going to be in the middle of those two segments. So I'm going to go with the triangle DMC is congruent to. Now, as soon as I establish an order, D has to match angle B. And then M has the same at the midpoint. And then we got to go back to A, which should match C. And those were congruent by angle, side, angle congruency theorem. Now, once the triangles are congruent, now we can get the pieces that we wanted to get congruent. Remember, we wanted to prove that this length here is the same as that length there. Well, we know that AM has to be exactly the same length as CM because they are corresponding parts of congruent triangles. Once I get these two triangles to be congruent, then their matching parts must be congruent. And that's one of the parts we wanted. The other part we wanted was that this segment here from D to M had to be the same as B to M. So B to M must be congruent to C to M because they are corresponding parts of congruent triangles, which means they're congruent. So now what I've done and what we've been able to prove is that this segment here is the same length as that segment here. Well, if those two segments are the same in length, then M has to be in the middle of that, and this diagonal then was bisected. And the same thing for this one. This line had to get cut in half because those two segments are equal. So what we're looking at is that M is the midpoint of each diagonal. And that's the definition of a midpoint. The midpoint has to lie right in the middle or cut the two pieces in half. Or if you wanted to, and as I'm going to follow up here, since it's the midpoint, that means the diagonals must bisect each other. So the diagonal A to C bisects the diagonal BD by definition of a bisector. A bisector must cut the two segments in half, which means M is going to be right in the middle. You probably could get rid of this step where I said M is in the middle by definition of midpoint, and just use your definition of bisector as well. But that finishes up our fourth property that we needed to prove on parallelograms. Now, all four of those parallelogram properties are going to trickle down that tree into everything else that was directly below it. So everything that we just proved about the parallelograms are true about rectangles, rhombus, and squares.